LeetCode 1872, Stone Game VIII. It is marked hard, and 71% of submissions pass. That acceptance rate is the clue. The hard part is not the code. It is seeing what the state actually is. The rules. Pick a number greater than 1, remove that many stones from the left, score their sum. Then put a single stone worth that sum back. The row shrinks every move, and the game ends at 1 stone. Alice takes the first 4. -1, 2, -3, 4. That sums to 2, so she scores 2. Bob is left with 2 and -5. He must take both and scores -3. 2 minus -3 is 5. Alice wants the difference as large as possible. Bob wants it as small as possible. Both play perfectly. Now read the constraints. N goes to 100,000. That single number rules out most of what you might try. So the real question is what the state is. What do you actually need to know to decide the rest of the game? The merged stone on the left is always the sum of everything removed. So the only thing that varies is how many are gone. Build prefix sums. Pre at I is exactly what you score if you take everything up to index I in one move. So a move is not really about stones anymore. It is picking an index and collecting the prefix sum at that index. Define f of I as the best difference for whoever moves next. You pick a j, score pre at j, and hand over f of j. The minus sign is the whole trick. Because it is a difference, one function serves both players. No turn flag. The base case is the end of the game. 1 stone left, nobody can move, so the remaining difference is 0. Trace it. F of 4 is 0, f of 3 is -3, and from there it settles on 5, which is the answer. That is a correct solution. Written directly, it is also far too slow, and this is where most submissions die. Here is the direct version. For every I, scan every j to its right. That inner loop is the problem. Every index scans everything to its right. That is n squared over 2 steps, about 5 billion at the limit. Measured, not guessed. 1,000 items takes 45 milliseconds. 8,000 takes 4.4 seconds. Look at the ratios. Every time n doubles, the time roughly quadruples. That is the fingerprint of quadratic. Extrapolate that curve to 100,000 and you get 687 seconds. 11 minutes. The judge gives you a few seconds. So this is not a slow solution. It is a solution that never finishes. Now look at that inner loop again because it is doing the same work over and over, and it does not have to. F of I wants the maximum over everything to the right. F of I -1 wants the same set plus one more item. It is a suffix maximum you already computed. So keep it in a variable and update it once per step. The entire inner loop becomes one line. That is the whole optimization, and it changes the complexity class. Here is the finished solution. Prefix sums, 1 variable, 1 backward loop. 7 lines of Python. Best starts at pre of n-1, because that is the last index, where f is 0 and the term is just the prefix. All 3 examples from the problem come out right. 5, 13, and -22. And I checked it against the slow version on 500 random arrays. 0 disagreements. Side by side at the same sizes, the fast version is 300 to 1300 times quicker. At the full constraint, the fast one finishes in 39 milliseconds. The slow one would still be running. Same recurrence, same answer. The only change is that the suffix maximum is carried instead of recomputed. That is the pattern worth taking away. A maximum over a suffix that only grows by 1 item is a single variable. 2 edge cases. With 2 stones Alice is forced, and the answer is the total. All negative values are fine too. If your solution has an inner loop recomputing a maximum over a suffix, that is where your time limit is going. It is filed as hard, and the finished code is 7 lines. The difficulty was in the reduction, not the typing. Every number here was measured on Python March 12, 13, not estimated. Daily problems solved properly. See you tomorrow.